Hi there, my name is Vince Haralabidis, and in this video we will learn how we can identify the number of solutions of a linear 2x2 system without solving that. And remember that we will talk about the number of solutions, not the exact solution, if any. To begin with, let's write down the general form of such a 2x2 system. The general form of a linear 2x2 system would be the form ax plus by equals c and a prime x plus b prime y equals c prime. By taking a look at this general form I just wrote, we can see that, okay, we have the x's and y's. It is, after all, a system 2x2 means two unknowns, in this case, x and y, and two equations. And I used as coefficients the ABC and the A prime, B prime, and C prime. The reason I did not use any further letters like D, E, and F, and instead I used the primes of the already used letters A, B, and C is simply because I want us to relate them. You can see that A and A prime refer to the coefficients of x's. B and B prime refer to the coefficients of y's, and C and C prime refer to the constant terms. And we will be working with these relations, with the blue values, with the green, and with the yellow ones. Before that, let's see what we expect. We know that any form ax plus by is c is basically the standard form of a line. So here, in such a system, we have two lines. When we call solution to a system is the point, the pair of numbers x and y that satisfies them both. Geometrically, that would mean the point that is common in both lines. So actually, when we try to algebraically solve such a system, it's the same as if we try geometrically to find how many common points these two lines have. And this leads us to the thought that in how many ways can we actually put two lines on the same, in the same plane, on the same piece of paper? We could have them like this. Here we can see that the lines are parallel. With regards to the common points, this means that no common points. So this would mean that we have 0 solutions. Another way would be this, L1 and L2. Here we can see that lines intersect. With regards to the common points, we can see that we have one common point, which means that we have one solution. And finally, we could have it like that. This is L1 and L2 is exactly on top of it. Here, we would say that lines are identical. This, with regards to the common number of common points, would mean infinitely as many common points, which would mean that infinite solutions, infinite number of solutions. So in general, when we have a system, a linear system, 2x2 of two equations with two unknowns, we expect that we should either have 0 solutions, no solutions, or one unique solution, or infinitely as many. Now, the question remains, how can we test that without the need of solving it? Well, like I said in the beginning, we will have to play with these values, A, B, C, and their primes. And from theory, we know that if A over A prime is equal to B over B prime and is also equal to C over C prime, we have infinitely as many solutions. If A over A prime is B over B prime, but they are different from C over C prime, we have 0 solutions. And thirdly, if A over A prime is different than B over B prime, we don't have to check what happens about the ratio of C over C prime. We can say that we have one unique solution. But remember again that we know that there should be one unique solution, but we still don't know the exact solution. Let's see some examples. 3x plus 2y equals 6. 6x plus 4y equals 12. Let me highlight them again. These are the coefficients of x. These are the coefficients of y. And these are the constant terms. To determine what happens in this case, it's all about the ratios formed. Look, we can either keep the numbers of the first one over the numbers of the second one, or vice versa. What seems easier to us? Here, for me, it seems easier to do the numbers of the second one, of the one below, over the numbers of the top one. So I would go and say 6 over 3 is 2. 4 over 2 is 2. 12 over 6 is 2. All of them ended up to the same answer. This means infinitely as many solutions. Another example, 5x plus 25y equals 10. And then x plus 5y equals 3. Again, let's highlight them. These are the constants. These are the coefficients of y, and these are the coefficients of x. Theoretically, here there should be 1. 5 over 1 is 5. 25 over 5 is 5. 10 over 3 is 3 point something. The ratios of the coefficients of x and y ended up to the same number, which is a number different than the ratio between the constants. So, based on the above theory, we know that here there should be 0 solutions. And finally, 2x plus 3y equals 7, x plus 10y equals 9. Again, let me highlight them. 2 and 1. Here, 3 and 10, the coefficients of y's, and 7 and 9, the coefficients of constants. 2 over 1 is 2. 3 over 10 is around 0.3. They are different. I don't even need to check 7 over 9. I know that here there should be one unique solution. Before we end up this video, I want you to remember that for this method to work, both lines should be firstly written in standard form, which means that if we have this, y equals 2x plus 9, and 3x plus 5y minus 10 equals 0, I need to firstly bring them both in standard form. Standard form means both x's and y's on the same side. So it should be y minus 2x equals 9, and then 3x plus 5y equals 10. But that's not yet enough. Yes, I found them both in standard form, but I want them to be on the same column. The same column should be x's, then y's, then constants. So I'm gonna rewrite them first as minus 2x plus y equals 9, 3x plus 5y equals 10. Now I can determine the values. These are the constants. These should be the coefficients of x. Let me write that again. These are the coefficients of y's. So now I can do minus 2 over 3, or it would be better if I have it written as 3 over negative 2, which is minus 1.5, 5 over 1, which is 5. They're not the same, which means that this leads to one unique solution. That is all. Remember, both in standard form, all of them in columns, x's, y's, constants, and then we basically work with the ratios. That's all for now. I hope I helped. I hope it makes sense. If you have any questions, put them as a comment below, and I'll see you all in one of the following videos. As always, thank you for your time.